So you want to go on a road trip. You and your friends want to go from, say, Baltimore, Maryland, all the way over to Los Angeles to visit some friends during spring break. Okay? And you're not a very rich college student, so you got to have enough money to get there and back. Well, you Google it and you find out that it is 3,210 miles on the road. And you know that your car is going to get 28 miles per 1 gallon of gasoline. Okay? And you also know that across the United States, the average gas price is about $3.25 for 1 gallon of gas. So now the big question is, do I have enough money to get there and back? Well, we got to calculate out how much money it's going to take to travel 3,210 miles. Now, there's a really simple, easy way to do this. These are not fractions. These are factors, they're ratios related to each other. So I can take this actually and I can say, well, that 28 miles equals 1 gallon of gas. And I can also take this and say that $3.25 equals 1 gallon of gas. Now you'll notice that gallons are the same. So what I can do is I can take this whole thing and create one long equation. 28 miles equals 1 gallon of gas equals $3.25. All of these things, even though they have different units, are equal to each other. So now the question is, how much is it going to cost me to go 3,210 miles? And I want to change that into dollars. How many dollars will that be? Well, I've got to multiply that by some factor that will convert miles into dollars. And in order to do that, I need to have miles on the bottom, my bottom unit. And that will be 28 miles taken from this three-way equation right here. And I need to have dollars on the top so that when this gets multiplied by dollars and divided by miles, the miles will cancel out, but I need to have $3.25 on the top. So now to do the math, I would take 3,210 times $3.25 divided by 28, and I will get, I don't know, I need a calculator. $372.60. $372.59. Now, if we round that off to according to significant figures, we would probably just call that $370 about. Okay, before we really get into talking about moles, we're going to be talking about relative masses. Now, what does that mean? Well, here I have a ping pong ball, and here I have a tennis ball. Now, if I were to say the ping pong ball had a mass of 1, the tennis ball would have a mass of 8. They have a 1:8 ratio. Okay? Now, suppose I had 2 tennis balls and 2 ping pong balls. What would the ratio of their masses be? It would still be 1:8, even though I've doubled the number of balls. Okay? What about if I had 6 ping pong balls and 6 tennis balls? What would the ratio of the masses be? It would still be 1:8. Okay? So what the big takeaway here is that if I have the same number of ping pong balls as I do tennis balls, the ratio of their masses would always be 1 to 8. And conversely, what I can say is that if I have 1 pound of ping pong balls and I have 8 pounds of tennis balls, there would be the same number of balls in each pile. Okay? If I had 1 ton of ping pong balls and 8 tons of tennis balls, there'd be the same number of balls in each pile. So where does that take us? Well, that takes us back to John Dalton's original idea of the atomic theory, developed around 1800, 1805, something like that. Now, they didn't know anything about protons, neutrons, and electrons at the time. In fact, his idea was not taking off very well. He just thought that atoms were just small, indestructible things. And John Dalton at the time then started working on the relative masses of atoms. He knew that the hydrogen atom was the lightest atom that there was around, and he gave that a mass of 1. They had no idea of protons, neutrons, and electrons. And he knew other atoms had a mass 8 times that amount. Okay? And he started collecting data. So that brings us into about 1870, when Dmitri Mendeleev in Russia developed his first iterations of the periodic table. We call him the father of the periodic table. We'll talk more about that later on. But here's one of his versions of it. And you'll say, well, that doesn't look anything like the periodic tables of today. Here's a periodic table of today. But they are. They're very, very similar. You'll take a look at this. He has lithium, sodium, potassium, rubidium, and cesium. He has in one row. Here they are in a column. Lithium, sodium, potassium, rubidium, and cesium. Okay? Here they had the relative weights. 7, 23, 39, 85. That's about 7. That's about 23. That's about 39. And that's about 85 and a half. Okay? So they're very, very similar. They didn't know anything about protons, neutrons, and electrons at the time, but they knew that these relative weights would react together. And they knew that one relative weight of hydrogen had the same number of atoms as 7 relative weights of lithium. Well, we're back to moles again.
Oh, yes, here I am. Hello, hello, hello.
We're talking about chemistry moles today, though, Mr. Mole.
Chemistry. I know all about chemistry.
Do you know what the word mole means in Latin?
No.
Well, that's the word that chemists use. The word mole in Latin means lump or heap.
Are you calling me a couch potato?
No, I'm not talking about you. I'm talking about the chemistry moles.
Well, let's go talk about chemistry moles then.
Okay, so we know that the Latin word for lump is mole. So chemists wanted to work in lumps. So they're back to the relative weights now of the elements. We could say that 7 pounds of lithium has the same number of atoms as 11 pounds of boron or 12 pounds of carbon, but that's quite a big lump. Chemists like to work in smaller lumps. So the metric system was coming into vogue at the time. Actually, it was in vogue for about almost 100 years at the time. And they decided to use grams. So where does that leave us? Well, if we take a look here, sulfur has 32 grams. So there would be 32 grams of sulfur. That would be what we call 1 mole. Iron up here would be 56 grams. So there would be 56 grams in 1 mole. Aluminum right here would be 27 grams in 1 mole. Now these bottles all have different numbers of grams in them. 32, 56, 27, but they all have the same number of atoms in them because they're relatively based. So where does that take us? Well, chemistry isn't just about studying atoms. It's about studying compounds also. So anyways, let's go back one step. We've got one mole is equal to the atomic weight in grams. But once again, chemists aren't just studying elements all the time. They study compounds. Compounds like sodium chloride, good old table salt. What does this formula tell us? It tells us that there is one sodium atom in there. Actually, ion, but we'll get to that later. And one chlorine. Okay? There's one of each. And if we look at the periodic table, sodium comes in at 23. And chlorine, right here, comes in at 35.5. Now we need to add these together. If we add these two together, we get 58.5 grams. There's 58.5 grams of sodium chloride. That has the same number of particles in it as 27 grams of aluminum. Okay? So what about something a little bit more complex? What about something like calcium sulfate, CaSO4? Well, let's take a look at that. This formula tells us we have one calcium, there's one sulfur, and there are 4 oxygens. It doesn't matter how you lay them around right now, but this gives you a visualization of what this looks like. Now, if we use the modern atomic periodic table, this one, we're going to see that calcium has 40.08. So we're going to write in calcium at 40.08. Sulfur is 32.06. So we're going to write that one in as 32.06. And oxygen is 16.00. There's one of those. 16.00. There are 2 of those. There's 16.00. That's 3 of those. And finally, here's the 4th one at 16.00. Now, if I add all of those together, I add 40.08, 32.06, 16 plus 16 plus 16, I get a grand total of 136.14. In other words, there would be 136.14 grams in 1 mole. Okay, so let's extend our definition of a mole a little bit. A mole also equals the molecular weight in grams. So the story so far now is that a mole is a lump, okay? And we said that it was equal to the number of grams in the atomic weight. So the atomic weight in grams. Weight in grams. So chemists dealt with that for a long time, but they were always wondering, well, how many atoms are in that lump of iron? Or how many atoms are in that lump of sulfur? We know it's the same number, but just how many is that? That number evaded people for a long time. It wasn't until about the 1915, 1920 or so, after Millikan had performed his famous oil drop experiment, that scientists finally had some numbers that they could work with. They knew the charge on one electron, and they knew the charge of a mole of electrons, so they could just divide it out. And here's the number they came up with: 602 billion. A billion has 9 zeros. Trillions. A trillion has 12 zeros. So 600 billion trillions. That's a freaking huge number. And you saw how long it took me to write that out. Well, nobody wants to sit there and write out that number all the time. So scientists and engineers and other people, all kinds of people, use scientific notation. We say, let's put that into scientific notation where we put the decimal point here. All right? The decimal point was originally here, so we had to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 times. So that number is 6.02 times 10 to the 23rd. I'm going to just call them particles now for this. It could be giraffes. So now we have a new part to this equation. We have 6.02 times 10 to the 23rd particles equals 1 mole. But we also know that a mole equals the atomic weight in grams. Okay? Now these particles can be atoms or molecules. Well, in this case, if we're dealing with the atomic weight in grams, we're going to call these particles atoms. But what about this one? 6.02 times 10 to the 23rd particles equals 1 mole. And we also said that that was the molecular weight in grams. So what are the particles this time? The particles this time are molecules. And this is where students get really ticked off at chemists. Why? Why did they ever do that? Why did they have mole and molecules? Don't get those two terms confused. That's a hard part for students, but that's something you need to be aware of. A mole is a lump. Molecule is Latin for tiny lump. And now you can go on to watch the next video by Dr. Slaybaugh.